Am I audible?
Yes, ma'am.
Okay. Waiting a few minutes. Only 43 students have joined till now. Okay, just waiting. I am calling only the absent roll numbers. 25, AMB 25, sorry, AMB 25, AMB 28, AMB 28, CB 78, CB 78, CB 91, CB 91, CB 92, CB 93, CB 95, CB 95, CSB 58, Computer Science 58, Computer Science 60, 60, 60, Computer Science 61, 61, Computer Science 63, 64, Electrical Engineering 56, 56, Electrical Engineering 56, Electronics 35, ETB 35, Electronics 35, 36, ETB 36, Electronics 41, 41, 41, Electronics 42, ITB 58, ITB Information Technology 58, Mechanical Engineering 49, Mechanical Engineering 51, Metallurgy 3030, Metallurgy 3030, Mining 26, Mining 26, Mining 27, Mining 27. All the students are absent. I have called only the absent roll numbers. That means remaining students are present. Okay. Now I will start my topic.
Oh, ma'am, this is ETB 036. I am present. I joined late due to network connection error, ma'am.
ETB 036.
Yes, ma'am.
Okay.
Ma'am, ma'am, AMB 026 is present.
AMB 026. Yes, I have given. Why are you
Yes.
calling? Why are you telling me? Okay, I think I have taken record of all these present students now. I will start. Is it visible?
Yes, ma'am.
Okay,
Yes, ma'am. This is visible.
okay. Just you see, today I will discuss on this Bessel's equation. The standard form of Bessel's equation is given by this. You see, x square d2i dx2 plus x dy dx plus x square minus n square, where n is a non-negative real number. Okay, non-negative real number. Okay, and here x equals to 0 is a singular point, no doubt about it. And most important thing, actually, you just observe the general solution. Only you see the solution. It is not, actually we did not deduce the solution. Just you take this as the general solution. Okay. The general solution is given by this. N is not an integer. The general solution is given by this, where y1 equals to this, and y2 equals to this. Just to note this as the solution, general solution, where a, b are constants, and the general solution is given by this. Y1, y2 are given by this. Now, if we multiply this y1 by this constant, suppose this is a constant, you see, just this is a constant. Gamma means, you know, beta and gamma function, I think it is known to all of you. So, if we multiply y1 by this constant and denote the function by jnx, denote the function by jnx. Actually, we need this. Actually, we need in this chapter, jnx is this, which is called Bessel function of first kind of order n. This is required in this chapter, jnx, which is called the Bessel function of first kind of order n. Okay, and if n be not an integer, okay, then the another solution is given by this, j minus nx. You see, if jnx is given by this, then j minus n, that means n will be replaced by minus n will be replaced by minus n, and so it should be given by this. In the case when n is not an integer, so the solution can be rewritten as this, where a1, b1 are constants, and the solution can be written as this, y equals to some constant jnx plus another constant j minus n x. Okay, again you see jnx is this, you may express jnx in this form, compact form actually, some using the summation notation. Actually sometimes we need this form also. So we just know the form of jnx, either this or this. Okay, jnx equals to this if this is actually expansion, and now jnx can be written by using the summation notation like this. This is an infinite series which can be written in by using this summation or sigma symbol, that is this. So I think you should remember what is jnx. Okay. Now actually we are to prove some recurrence relations. These are all important. How to prove? Thus, here you will observe that some algebraic computations will be done. These are very easy to prove, but some algebraic computations will be done. Because we know J and X, so we can differentiate J and X with respect to X. And if n is replaced by n minus 1, then you can obtain Jn minus 1x. Again, in order to obtain, suppose in some problems you need Jn plus 1. I think what is Jn plus 1? That is also known to you because Jnx is known. So we first prove this recurrence relation. Xjn dash x equals to this. Xjn minus 1x minus n jnx. So you see jnx equals to this. And in order to compute Jn dash x, we have to differentiate Jnx with respect to x. Then what we obtain, you see, Jn dash x means differentiate with respect to x. So that this part will remain unchanged. This is constant. Since we have to differentiate with respect to x, only this term will be differentiated, right? So it should be x by 2 whole to the power n plus 2r minus 1. And if you differentiate x by 2 with respect to x, then there will be some constant half. But other terms remain unchanged because these are all constants. Minus 1 power r. This term will remain unchanged. All these are constants. So Jn dash x will be equal to this. I think it is clear, right? Clear. It is all. I think it is clear to all of you, right? Just you differentiate j and x with respect to x. So just x by 2 whole to the power n plus 2r will be differentiated, but other terms, other multipliers will remain unchanged. Now we have to compute x j n dash x. X j n dash x means just we multiply this with this which we have differentiated j and x with respect to x, which is obtained by differentiating j and x with respect to x. Now it will be multiplied by x. So you see there is half, and if it is multiplied by x, then another x by 2 will be formed, and this is x by 2 whole to the power n plus 2r minus 1, another x by 2. Then this product will be like this, n plus 2r, product of these two terms. If we multiply by x, then x by 2 multiplied by x by 2 whole to the power n plus 2r minus 1, that will be actually x by 2 whole to the power n plus 2r. But other terms remain unchanged. Now you see here it is, you see n plus 2r. Okay, now we can write here 2n plus 2r minus n. N plus 2r may be rewritten as this 2n plus 2r minus n, because 2n minus n means actually n. So this n, just this n is replaced by 2n minus n. So n plus 2r will be expressed in this form. Okay, now you see if we take common 2 from this factor, 2 into n plus r, and just you break this into two sums like this by this into this minus n by this into this, like this, you see, and it looks like this. Just you break this sigma into two, this sum into two groups like this. Another first containing this n plus 2r, another is minus n, this, like this. Then what happens, you see, if you just write down this gamma n plus r plus 1, which is actually n plus r, gamma n plus r, right? Gamma n plus r plus 1 is actually n plus r, gamma n plus r. Okay. So you see, if we just you cancel these two factors, n plus r, then what happens? If we cancel n plus r from numerator denominator, then the denominator becomes r factorial gamma n plus r, but this n plus r will be cancelled. And now you see x by 2 n power n plus 2r may be written as x by 2 into x by 2 power n minus 1 plus 2r. Okay, that's actually product of these two will be n plus 2r only. Now here gamma, you see n plus r is written as minus 1 plus 1. Just you see minus 1 plus 1. Okay, the second term remains unchanged, you see. Then what happens, you see, this is x by 2 whole to the power n minus 1 plus 2r, and now you see 2 will be cancelled. These two will be cancelled and x is taken outside this summation like this. This x is taken outside the summation symbol, but other terms remain unchanged. Okay, here this x is taken outside the summation symbol. 2 has been cancelled from numerator and denominator. And now you see this is minus 1 power x by 2 whole to the power n minus 1 plus 2r, and the denominator is like this. You see, if you compare this with j n x, then it is n minus 1, so it should be j n minus 1x. But you see, just you compare this with this. What is the difference between this and this? What is the difference? You see here n minus 1, and but it is n in the second term. So it is j n x, n j n x, and this is actually x. You see x, and this is given by j n minus 1x. This is actually j n minus 1x. Already I have told you what is j n x, and that is important. You just note this. J n x is given by this, and if n is replaced by n minus 1 here and also here, then it should be replaced by j n minus 1x. If you observe that this is n plus 1 and here this power is n plus 1, then this n on the left side should be replaced by n plus 1. So we have proved this first relation. Second relation, we have to prove that x j n dash x equals to n j n x minus x j n plus 1x. You see j n x is given by this. Already we have observed this. Again, you have to calculate j n dash x. So differentiate with respect to x like this. And so you will obtain this. Now you see again you have to compute x j n dash. You see what is the difference between these two? Here it is, you see, x j n minus 1x minus n j n x. As per requirement, you have to calculate. You see here it is n j n x minus x j n plus 1x. Okay. So first you calculate j n dash x. So differentiate j n x with respect to x. Then we get this. We get this. Then we multiply this by x. Again you multiply this by x. And so this is half. It becomes x by 2, which is this. But this factor remains unchanged. Other terms remain unchanged. Only x is multiplied here on the left. That means it has been multiplied on the right side also. And so half now becomes x by 2. Now you see here x j n dash x equals to, you see x by 2 whole to the power n plus 2r minus 1 and this x by 2. And so it will be actually x by 2 whole to the power n plus 2r like this. And now we break this n into this plus 2r into this. Okay, like this. You see, just you break this single term into two groups. N into this plus 2r into this, like this. Like this, you see, just like this. Okay. Now you see the first term becomes n. This n can be written outside the summation symbol n j n x. And this second term can be written as x. You see here actually you may write x by 2 whole to the power n plus 2r minus 1 into x by 2. And 1x is written here. Therefore it is half only. Okay. And then you see also you see that in this term r varies from 0 to infinity, but here r varies from 1 to infinity. R varies from 1 to infinity, otherwise it will be negative, which is impossible. So r varies from 1 to infinity. Okay. In the second term, that means this, in this term, in the summation you observe that r varies from 1 to infinity. Okay, now this term remains unchanged, which is n j n x plus x into, you see we have used some transformation like this, r minus 1 equals to s, r minus 1 equals to s. And so if r equals to 1 to infinity, then it becomes s equals to 0 to infinity. Now you see the second term may be written as this, which is actually n plus 2s plus 2 minus 1 is actually 1. So it is n plus 1, n plus 1. So it is actually j n plus 1x. If just observe this term and this term, then it is very clear that this is j n plus 1x and this is n j n x. And we have started with x j n dash x. So we have proved here that x j n dash x equals to this. Okay, now we prove another relation 2j n dash x equals to this. Okay, and if you observe this, then this is obtained directly by adding the recurrence relations 1 and 2. Already you have proved x j n dash equals to this, and also you have proved in the first case, you have proved this equals to this, and if we add 2 and 3, then you will obtain this, and then just use cancel x from both sides and obtain this relation, and hence it is proved. Another relation we have to prove is this. You see, if you subtract 3 from 2, you just will subtract 3 from 2, that means from this, then what we get? We get, you see, this, sorry, you see this, subtracting 3 from 2, we get this, just we get this, and then just simplify this and obtain this relation. So it is proved very easily. Subtracting 3, equation number 3 from 2, we can prove this very easily. Okay, another proof you see, just you see. What is their observation? ddx of this product of 2 x to the power n j n x. Okay, so you see, if you differentiate this product, then first you differentiate x to the power n with respect to x, then it is n x to the power n minus 1 j n x, plus you see x n into derivative of the second term, that is j n dash x. Now already you have computed j n dash x, so you can use 2. We can use 2 here. J dash equals to j n minus 1x minus n by x j n x. We can use this value of j n dash x here. You see, just you see j n dash x here using this. Just you write here x to the power n minus 1. Then it is written as x into j n dash x. And then we can use 2 to obtain the value of x j n x. Okay, and this is x j n dash x is given by this. This is x to the power n minus 1 into x, and x j n dash x is replaced by this using 2. But other terms remain unchanged. Just you observe the other terms remain unchanged. So you have proved here ddx of x to the power n j n x equals to this. Okay, x to the power, you just simplify this and obtain the relation. N x to the power n minus 1 j n x, you see, and this is n x to the power n minus 1 j n x, so these terms will be cancelled. Only non-vanishing term is x to the power n minus 1 into x into j n minus 1x, so it is x to the power n j n minus 1x. Is it clear? Is it clear?
Yes, ma'am.
Am I okay? Okay. Am I
Yes,
audible?
ma'am. Yes, ma'am.
Okay.
Yes, ma'am.
Screen is clearly visible, I think.
Yes, ma'am.
Yes.
Okay. We can prove, alternatively, we can prove this. Okay. Just you see. Now, first of all, you note this, everywhere you should know what is JNX. Right? JNX should be known. Otherwise, it is not easy to prove. JNX should be known. If it is JNX, now you see x to the power n, jnx will be differentiated with respect to x. You see x to the power n, jnx is this. That means we should multiply jnx by x to the power n. So it should be x by 2 whole to the power 2n plus 2r. Sorry, x to the power 2n plus 2r. If we multiply by x to the power n, then it should be x to the power 2n plus 2r, right? But denominator is 2 to the power n plus 2r. Okay. Then you have to differentiate with respect to x like this. Just differentiate with respect to x. Then x to the power 2n plus 2r should be differentiated with respect to x. Then what happens? This will be the derivative. No doubt about it. 2n plus 2r x to the power 2n plus 2r minus 1. It is very, very easy to differentiate with respect to x. Now you can take common 2 from these two. Then what happens? It is 2 to the power n plus 2r, cancelling 2 from numerator and denominator. The denominator should be 2 to the power n plus 2r minus 1, like this. But other terms remain unchanged. This will remain unchanged. Now it may be written as x by 2 whole to the power n plus 2r minus 1. You see x power this, 2 power this, same power. So x by 2 whole to the power n plus 2r minus 1. And this is actually gamma n plus r, and n plus r should be cancelled from numerator and denominator. N plus r. We should cancel this. And then finally we get this. And so we can write this as n minus 1 plus 2r. The denominator should be written as n minus 1 plus 1. And everywhere you see n minus 1, n minus 1. So it is jn minus 1x. And hence it is proved. Actually it is proved independently. Here we have used using 2. We have used 2. But here we have proved independently. Okay, and you may choose any method. And you can use any algebraic calculation. So you have freedom to use this, to calculate this, to prove these relations. Another relation you have to prove. I think I have told these things, na? Yes, alternative proof, it is done. Now you see this. ddx of this, x to the power minus n, jnx equals to this, you see. First of all, you write jnx equals to this. And then you see you have to multiply jnx by x to the power minus n. So we should append this. X to the power minus n, so it is x to the power n plus 2r minus n means x to the power 2r only. Like this. And the denominator is 2 to the power n plus 2r. And r factorial gamma n plus r plus 1. Now you have to compute ddx of this. Like this. If you differentiate with respect to x, then what happens? You see, just x to the power 2r, only term containing x, and differentiate with respect to x means 2r x to the power 2r minus 1. And other terms remain unchanged. Now r factorial may be written as r into r minus 1 factorial. And then you see, this term remains unchanged. R minus 1 factorial remains unchanged. Just r will be cancelled. From numerator and denominator, r will be cancelled. Okay, and r minus 1 factorial will remain unchanged. Now there is another 2 in the numerator. So after simplification, it should be 2 to the power n plus 2r minus 1. Like this. If we use this transformation, r minus 1 equals to s, then you should get this. Oh, sorry. There is some typographical error. I will check. I will actually rectify this. Okay, now it will be s, not r. Yes, it is correct. It is now correct. But here it should be s equals to 0 to infinity. Because we have used this transformation, r minus 1 equals to s, and r equals to 1 means s equals to 0. And these are limits of s, therefore it should be s equals to 0 like this. It is correct, but it was not correct. Okay, I will correct it and then I will send it. Then finally we will get this. Now you see x by 2, power is the same, n plus 2s plus 1 like this. And now n plus s plus 2 may be written as n plus 1 plus s plus 1. What you should observe? It is n plus 1. Again in the denominator in gamma function, the parameter, yes, you see n plus 1. So it is jn plus 1x like this. Jn plus 1. Because n is replaced by n plus 1 here and also n is replaced by n plus 1 here. So jn should be replaced by jn plus 1. Another proof you see. ddx of this equals to this. Now ddx of this is actually, you see here, if you write here x to the power minus n into x to the, just you see x may be replaced by x to the power minus n into x to the power n plus 1. Then actually product of these two will give x to the power 1. Now why is it written here? Why we write this term in this way? Because we know ddx of x to the power minus n jnx already we have computed. Okay, now you consider this as product of two functions. First of all, suppose this is, this is u and this is v. And so we differentiate v with respect to x, where u remains unchanged. So x to the power minus n jnx remains unchanged. And we differentiate this with respect to x like this. Then you see plus, this will remain unchanged like this, and we should differentiate the first term u with respect to x. So ddx of this like this. Now ddx of x to the power n jnx already we have computed. This is this. Okay, but here you see this is x to the power n plus 1 jn plus 1x. We have computed ddx of x to the power n jnx equals to this, but changing n to n plus 1, what we get? Ddx of x to the power n plus 1 jn plus 1x is given by this x to the power n plus 1 jnx. So I think it should be replaced by x to the power n plus 1 jnx. Another thing, ddx of x to the power minus n jnx we have already computed, and that is given by this. So using these values in 1, from 1, what we get? ddx of this equals to this and this. All these values have been substituted. And now we simplify jnx into jnx, jn square x. And x to the power n plus 1 minus x means x only. So we take common x, and now it is jn square x. Now it is minus jn plus 1 square x, like this. Another relation you have to prove, just you see, ddx of this. Okay, now ddx of jn square x is, you see, jn square x may be written as this, x to the power n into x to the power minus n, that is actually x to the power 0 jnx. So if you multiply this, then it will be jn square x. Just jn square x is written as this. Now we consider this as product of two. One, suppose u is this, we differentiate v with respect to x, then v remains unchanged, and you should differentiate u. Anyone may be written first and anyone may be written second, because this is plus, so you may change the order. Okay, here you see, first differentiate this term with respect to x, and this will remain unchanged, plus this will remain unchanged, and differentiate the second term like this. Okay, now you see the relation x ddx of x to the power n jnx should be replaced by this. And now you see, actually x to the power n jnx is this, and ddx of this already we have proved. Just use this 5 and 6. We have used these relations 5 and 6. We put these values obtained from 5 and 6, and then after simplification it will be like this. So ddx of jn square x equals to this. Okay, now you see, Okay. By using the recurrence relation 3, just you see 3, just a minute, just to verify. 3. 3 means, you see, where is 3? 3, 3. 3 means this. Okay, okay. 2jn dash x equals to this. Jn minus 1x minus jn plus 1x equals to 2jn dash x. Now you, yes. Okay, now it is replaced by, okay, okay, 2jn dash x. Okay, this is replaced by 2jn dash x using recurrence relation 3, and finally we just change n to n plus 1. Actually, all these things depend on the relation what you have to prove. Just you observe the relations what you have to prove and then you change accordingly. Okay, changing n to n plus 1 throughout. Actually, what is doing, what we are just doing now, change just n into n plus 1. Okay, changing n to n plus 1, what we get this, and then you add these two relations 1 and 2 to obtain this, because you are to obtain jn dash square x plus jn plus 1 dash sorry, jn square x plus jn plus 1 square x ddx of this, ddx of jn square x plus jn plus 1 square x. Okay, so it should be like this. Okay, already we have proved that jn dash x equals to this by using recurrence relation 2. So also jn dash x equals by using recurrence relation 1. Actually, we have proved so many relations and obtained from one relation 1, we can write this. From relation 2, we can write this. And changing n to n plus 1, we have obtained this. And substituting the values of jn dash x and jn plus 1 dash x from 4 and 5 in 3. Just we put the values of jn dash x and jn plus 1 dash x. Use these values obtained from 4 and 5. You see, from 4 you can calculate jn dash x. From 5 you can replace jn plus 1 dash x. And you see relation 3. Equation number 3 contains all these terms, jn dash x and jn plus 1 dash x. So we can use 4 and 5 in 3. Okay, and then we will obtain this. Just simplify this, obtain this. Okay, so depending on the relations what you have to prove, you have to change the notations, like n should may be replaced by n plus 1, n may be replaced by n minus 1. Sometimes it is required to differentiate. Actually, if you are to prove something, say not this, you see, in the first few cases you have observed that you are to compute derivative of jnx. Yes, in order to prove this, you see, most important thing is jn dash x. You have to differentiate jnx with respect to x. Similarly, in order to prove the first relation, first recurrence relation, again we have observed here jn dash x is present, and so we are to differentiate jnx with respect to x. So we first know what is jnx. After that, just we observe this recurrence relation and then you start what you have to do. Jn dash x, that means you are to differentiate jnx with respect to x like this. And then after simplification, you will obtain this. But note this, here jnx as well as jn plus 1x, and there is some minus sign here. So you just observe the terms required here. Jn plus 1 is required here. So we should write down the terms accordingly so that we can obtain. There exist actually so many methods to prove this recurrence relation, so you can use any method. All these are algebraic computations. Okay, all this actually you have already observed that some algebraic computations have been done. I have actually done all steps. Each and every step I have done here to help you, and I will send it by correcting some typographical errors if exist. After that, I will send it. Okay. Okay, may I stop presenting?
Yes, ma'am.
Okay, ma'am.
Okay. Thank you. Just now I leave.
Excuse me,
Yeah.
ma'am.
Yes, yes, yes.
Actually, I joined late. Can you help me present?
IT 58.
Yes, ma'am.
IT 58. Yes. Yes, now I.
Ma'am,
Thank you, ma'am.
ma'am, also I was joined late.
Computer science 61.
Yes, ma'am, Suman Kumar.
Okay, just. Yes, now I have given. Any more who have joined late? Any more? Please tell me who have joined late. Okay, nobody is there. I think I have finished the syllabus. So this may be last class. Thank you, all of you.
Thank you, ma'am.
Thank you, ma'am.
Okay.
Thank you, ma'am.
Okay. May I leave now?
Thank you, ma'am.
Thank you,
Okay.
ma'am.
Okay, okay. Thanks all of you. Now I leave now.